Hi, Dr. Tomardo. I will be presenting on the last topic that I have, so the topic of memory and learning, which consists of two main articles. The first of which is titled The Cognitive Neuroscience of Human Memory, since HM. So this is by Larry Esquire and John T. Whitsted. So the abstract of this article specifically is focusing on the work with HM that happened in the 1950s and established the key principles about the organization of memory that inspired decades of experimental work. So since HM, so there was the study of this man whom they removed like his hippocampus. And that is what launched the study of human memory and its disorders. It has continued to yield new insights into improved understanding of the structure and organization of memory. So this article specifically focuses on the review of this work and the emphasis on the list of these things here. The neuroanatomy of medial temporal lobe and diencephalic structures important for memory, and multiple memory systems, visual perception, immediate memory, memory consolidation, the locus of long-term memory storage, the concepts of recollection and familiarity, and the question of how different medial temporal lobe structures may contribute differently to memory functions. And so the anatomy of memory is essentially like the structure of memory, and it specifically focuses on the HM case study that revealed the function of memory is in the hippocampus. So the work with HM is sometimes cited incorrectly as evidence of the importance of the hippocampus for memory, but this particular point could not, of course, be established by a large lesion that included not only the hippocampus, but also the amygdala, together with the adjacent parahippocampal gyrus. So while the medial temporal lobe structures have received the most attention in studies of memory and memory impairment, it is notable that damage to the diencephalic midline also impairs memory. And so the principles of organization suggested by HM's findings. So the early descriptions of HM suggested four main principles about how memory is actually organized in the brain. So the first of which is that despite his debilitating and pervasive memory impairment, HM successfully acquired a motor skill. And so this finding raised the possibility that memory is not a single thing. And so the second principle is that because his memory impairment appeared to be well circumscribed, the structures damaged in the memory impaired patients were thought to not only be involved in intellectual and perceptual functions. The third of which, HM had a considerable capacity for sustained attention, including the ability to retain information for a period of time after it was first encountered. So the specific finding actually suggested that medial temporal lobe structures are not needed for immediate memory or for the rehearsal and maintenance of material in what would now be termed working memory. And so HM, in the last principle, appeared to have good access to facts and events from time periods remote to his surgery. And so this observation actually suggested that the medial temporal lobe cannot be the ultimate storage site for long-term memory. So permanent memory must be stored elsewhere, presumably in the neocortex. And so in the years since HM was described, each of these ideas has been a topic of extensive experimental work. And so this is an example of specifically those areas that the principles are referring to. In multiple memory systems, the memory impairment in HM and other patients is narrower than once thought in that not all kinds of learning and memory are affected. The first hint of this idea came when HM was found capable of learning a hand-eye coordination skill, mirror drawing, over a period of days. And so despite having no recollection of practicing the task before, he was actually able to learn the skill. So although these findings showed that memory was not unitary, for some time it was thought that motor skill learning was a special case, that all the rest of memory is of one piece and is impaired in amnesia. So subsequently, it was discovered that motor skill learning is but one example of a large domain of learning and memory abilities, all of which are intact in HM in other patients. So HM's motor skill learning marked the beginning of a body of experimental work that would eventually establish the biological reality of two major forms of memory. So with visual perception, The formal testing of patient HM over the years documented his good performance on intelligence tests and other tests of perceptual function and lexical knowledge. He could detect the anomalous features of cartoon drawings, and he performed above the control mean on the Mooney closure task, which requires patients or participants to find a face in a chaotic black and white pattern with incomplete contour. So this perspective specifically, that visual perception is intact after large medial temporal lobe lesions, was eventually challenged first by work in monkeys and later by studies in humans. So these studies propose that the perirhinal cortex, one of the structures damaged in HM, is important for complex visual perception tasks involving stimuli with substantial feature overlap. So it was also proposed that the hippocampus is needed when spatial processing is required, as in visual discrimination involving seeing. So there's immediate memory and then working memory. So the early descriptions of HM emphasize how capable he was at focusing his attention and at retaining information for short periods of time. So for example, he could retain a 3-digit number for 15 minutes by continuous rehearsal, using what would now be termed working memory. Yet when his attention was diverted, he forgot the whole of it. And so HM exhibited a marked discontinuity in performance as the string length increased. He repeated up to 6 digits correctly for his first try. 6 was his cooperative digit span. But he never succeeded in 7 digits, even though he was given 25 repetitions of the same string. The interpretation was that as short string lengths, HM could rely on his intact immediate memory, and that he failed when the material to be remembered was more than could be held in mind. So that is, he failed when the material exceeded his immediate memory capacity. So this demonstrated that time is not the key factor that determines how long information can be retained by patients like HM. The relevant factors are more so immediate memory capacity and how successfully material can be maintained in working memory through rehearsal. So remote memory and memory consolidation. A key insight about the organization of memory came with early observations of HM's capacity to remember information that he acquired before his surgery in 1953. So initially, he was described as having a loss of memory or retrograde amnesia, covering the 3 years immediately preceding the surgery and the earlier memories, quote unquote, seemingly normal. About 10 years later, the impression was similar, as there did not appear to have been any change in HM's capacity to recall remote events and antedating his operation, such as incidents from his early school years, a high school attachment, or jobs he had held in his late teens and early 20s. And so memory in the neocortex, the view that emerged from the study of HM in other patients is that medial temporal lobe structures are uniquely specialized to establish and maintain declarative memories. Other structures support the initial perception and processing of an experience, and these other structures are also critical for the long-term storage of that experience. So a long-standing view is that the cortical processing of a multisensory experience leaves a distributed record in the same multiple regions that initially performed the processing. So for example, neurons in visual areas store the visual aspect of a multisensory experience. Neurons in auditory areas store the auditory aspect of the experience. Other areas store the spatial aspects, and so on. So according to this view, any act of remembering consists of the coordinated reactivation of the distributed neocortical regions that were engaged at the time of encoding. And so when a memory is first formed, this reactivation depends on the hippocampus and then the related structures. But once memory is fully consolidated, reactivation can occur independently in the neocortex. So recollection and familiarity. In recent years, there has been extended investigation of the idea that different medial temporal lobe structures, the hippocampus, the entorhinal cortex, the perirhinal cortex, and the parahippocampal cortex, may support different memory functions. The study of HM could not address this issue because his bilateral lesions included most of these structures. So however, other patients, especially patients with limited hippocampal lesions, have been useful in this regard. One issue that has commanded considerable attention concerns the roles played by the hippocampus and pararhinal cortex in recognition memory. Recognition memory is thought to be supported by two processes, and these are recollection and familiarity. Recollection involves remembering specific contextual details about a prior learning episode. Familiarity involves simply knowing that an item was presented without having any available additional information about the learning episode. So according to one view, both the hippocampus and the pararhinal cortex contribute to recollection and familiarity. According to a different view, the hippocampus and pararhinal cortex selectively support recollection and familiarity, respectively. Group studies and multiple methods. So the study of patients and medial temporal lobe lesions, especially the severely impaired patient HM, has led to dramatic advances in understanding the structure and organization of memory. As work progressed, many studies came to focus on smaller lesions, less severe impairments. Many of these studies were based on single cases and investigated specific questions about particular aspects of impairment. For example, recall versus recognition, or recognition versus familiarity. Such questions are difficult to settle from individual case studies because the expected effects are relatively small. And so under such conditions, a deficit may reflect unmeasured, premorbid individual differences rather than the effect of a focal brain lesion. So accordingly, for many questions, single case studies are more suggestive than conclusive. And group studies are needed to answer experimental questions in a compelling way. So some of the big conclusions are that the elements of long-term memory are stored in the neocortex as products of the distributed domain-specific processing that occurred in different regions of the neocortex at the time of learning, which then creates this larger conclusion that long-term memory for whole events is widely represented, but the multiple areas that are involved each store distinct components of information. So acts of remembering involve the reactivation of the same neocortical regions that initially processed and stored what was learned. So the role of the medial temporal lobe is to consolidate the distributed elements of memory into a coherent and stable ensemble, a process that takes years. Many questions remain about how consolidation works, as well as memory storage, memory retrieval, and the specific functions of the different medial temporal lobe structures in the different areas of the neocortex. So all of these topics encompass what has become a substantial and fruitful tradition of research within systems and cognitive neuroscience. And it's a tradition that began with the study of HM. So this leads us to the second article that's titled Training and Plasticity of Working Memory by Torkel Klingberg. So the overview of this article is that working memory, or it's referred to as WM in the rest of the article, has a capacity working memory capacity predicts performance in a wide range of cognitive tasks. So although working memory capacity has been viewed as a constant trait, recent studies suggest that it can be improved by adaptive and extended training. So this training is associated with changes in brain activity in frontal and parietal cortex and basal ganglia, as well as changes in dopamine receptor density. Transfer of the training effects to non-trained working memory tasks is consistent with the notion of training-induced plasticity in a common neural network for working memory. The observed training effects suggest that working memory training could be used as a remediating intervention for individuals for whom low working memory capacity is the limiting factor for academic performance or in everyday life. And I think this is the main part where it connects to the impact into the classroom. And so explicit versus implicit training of working memory. So working memory refers to the retention of information over a brief period of time, a function that is of central importance for a wide range of cognitive tasks and for academic achievement. So impaired working memory is observed in any neuropsychiatric in many neuropsychiatric conditions such as traumatic brain injury, stroke, mental retardation, schizophrenia, and attention deficit hyperactivity disorder, so ADHD. It is thus not surprising that attempts to improve working memory have a long history. So in their 1972 article titled On the Theory of Practice of Improving Short-Term Memory, Earl Butterfield and colleagues reported a series of studies attempting to improve short-term memory in learning disabled students or individuals by teaching participants to use subvocal rehearsal strategies. So although this approach led to some improvement in the participants' performance, there was no evidence of transfer either to non-trained cognitive tasks or to everyday performance. So the psychological and neural correlates of working memory. So neurophysiological studies show that maintenance of information and working memory is associated with elevated and sustained neural firing over a delay when information is kept in mind. So neuroimaging studies in humans have mapped working memory related activity to both sensory association, cortices, and prefrontal cortex. So some of these regions show specificity to the sensory modality of the stimuli. And then other regions, including parts of the intraparietal cortex and dorsolateral prefrontal cortex, are activated across several modalities and thus reflect the multimodal type of activity. So individual differences in activity in both the intraparietal and prefrontal cortex are correlated to working memory capacity differences among adults, as well as when comparing children and adults. So neural network models have suggested that stronger frontal parietal connectivity is one potential mechanism behind higher working memory capacity. And so later on, when it speaks more to impact of classroom, I think this is a specific point of when we think of educators and what we could focus on in terms of developing better structures for the classroom, working on specifically this idea of the neural network models that create that stronger frontal parietal connectivity is, I think, what creates the better focus to build lessons that could help students develop a higher working memory capacity. So computerized training for working memory. An example of what might be termed implicit working memory training is a training program originally developed by Klingberg and colleagues for children with ADHD. This training involves repeated performance of working memory tasks with feedback and rewards based on the accuracy for every child. The effective training time is 30 to 40 minutes per day, 5 days a week for 5 weeks, which turns out to be about 15 hours. The difficulty of the task is adjusted during the working memory training on a trial by trial basis by changing the amount of information to be remembered so that it is close to the capacity of the subject, meaning that there is a development program so far, and there are studies that are focusing on how it is that working memory can be improved through a systematic way. Working memory training focusing on updating. So the training program described above, so the one that we just described, focus on training and increasing working memory capacity primarily by increasing the amount of visual spatial information that should be retained. So another approach to working memory training also uses the principles of implicit training, but focus specifically on updating, namely the replacement of old information in a hypothetical working memory store with new information. So the neural correlates of working memory training. Identifying the neural correlates of training-induced improvement has many caveats, since there are many parallel behavior changes occurring during the course of training. So furthermore, the aspects of brain activity associated with superior capacity are still a matter of debate. So the majority of studies indicate a positive correlation between working memory capacity and brain activity in task-relevant areas. Inter-individual differences in working memory capacity have been positively correlated with activity in the intraparietal cortex. The working memory capacity increase during childhood is also mainly positively correlated with brain activity in task-relevant areas of the intraparietal sulcus and prefrontal cortex. Conversely, the decline of working memory during aging is mostly associated with a decrease in activity although there might be different trends in different prefrontal areas. So in line with these results, the neural network models suggest mechanism by which higher EOLD activity would be associated with better capacity. So the concluding remarks. The research on working memory training reviewed in this article represents just the beginning of a new research field that explores the possibilities for enhancing cognitive functions by training. This field faces an even larger set of questions. So although plasticity is probably the rule, some functions might be more easily trainable than others. One study, for example, found the training paradigm used for working memory tasks did not work for training of inhibitory tasks. Another challenge will be to explore individualized training regimes whereby training on several cognitive tasks is combined and to investigate combinations of cognitive training with pharmacological treatment and physical exercise. So I think overall, when we think about the connection between these two articles, one being the foundation of memory and learning, not just specifically, or just like the neuroscience of it. And then the second article being focused on a specific strategy that is being used in terms of developing the working memory specifically through a computerized program. And well, as they're calling it, a training. What I think is interesting is that it's creating, I think, a sort of notion where when we think about it in the educational field and within a classroom, I think when we think of creating a training program for students in classrooms, it starts to become, I think, very, very difficult to try to conceptualize. And I mean, not even to mention, funding and capacities at schools. So I think what would be the most interesting aspect of this would be to see in which ways could the same neuroscience and information and what is being found through these training programs, how it could be adapted to all classrooms, because yes, it impacts or students with ADHD are whom the training programs are mostly geared toward. When we think about classrooms that have the need for working memory and capacity to be increased, I mean, that's everywhere. So I would wonder what it's going to look like moving forward. Thank you for listening to this presentation.